this video, I'd like to continue talking about the powers of complex numbers. And specifically, I'd like to look at two more example problems where we need to apply the formula that we derived in a previous video, where if we write our complex number in its polar form and we raise it to, let's say, the nth power, then this is equal to the magnitude or the modulus of that complex number raised to the nth power multiplied by this direction, where the angle theta, which is measured relative to the positive real number axis, is multiplied by n, whatever that exponent is. So the magnitude is multiplied by itself n times, and the angle is added to itself n times. And we call this de Moivre's theorem. And this theorem can be incredibly useful since if we try to take this number in its rectangular form and actually multiply it out 4 times, it would be very tedious. That is a way to check our work, but it's a very long process where this can be quite quick, especially when we already know the modulus and the argument or the angle of our complex number. So let's start by writing our complex number z in its polar form, where it's the modulus multiplied by the direction, which is just the cosine of the argument or the angle, 315 degrees, plus I times by the sine of 315 degrees. And if we weren't told what the modulus and the argument were, then we can find that for ourselves by just using the formulas. That the modulus of z is just the square root of the real part squared plus the imaginary part squared. And the angle theta is the inverse tangent of the imaginary part over the real part. And with this formula, we do have to be careful. If the number is not in the first or the fourth quadrants, we will either have to add 180 degrees, like for quadrant 2, or subtract 180, like for quadrant 3, so that we shift the angle to the correct angle, since this formula only gives outputs between minus 90 degrees and 90 degrees. But since we already know both the modulus and the argument, we can just immediately apply our polar form, and we are raising our complex number z to the 4th power, meaning that we will take its magnitude and raise that to the 4th power, and we will take the angle and multiply that by 4. So we get the cosine of 4 times 315 degrees plus I times the sine of 4 times by 315 degrees. And at this point, we just need to simplify everything. And 4 to the 4th power, that is 256. And this angle, 4 times by 315 degrees, is 1,260 degrees. Now, the angle is much greater than 360, but to get an angle between 0 and 360, we can just subtract 360 multiple times. And for this angle, we would actually have to subtract 3 different times, I believe. If we do it once, this brings us down to 900. If we do it again, then we're at 540. So we need to do that one more time. And this brings us to 180 degrees. So we can rewrite this z raised to the 4th power as 256 multiplied by the cosine of 180 plus I times by the sine of 180. And we know what the cosine and sine of 180 are. We can use the unit circle if we want, but we're talking about this point right here, where the x value or the cosine value is -1, and the y value or the sine value is 0. So this right here is -1, this is 0, and we would just get 256 multiplied by -1, which is minus 256, and we can see that would be choice letter C here. And let's do one final question. Let me scroll a bit over and let me paste the formula back in so that we can use that as a guide. And we're told that we need to take this complex number z and raise it to the fourth power, but we're told its modulus and its argument. So let's start by writing z in its polar form as 2 multiplied by the cosine of 60 plus I times by the sine of 60 degrees. And we need to take z and raise it to the fourth power, meaning we will take the magnitude and raise that to the fourth power. And we will take these angles and multiply them by 4. But 4 times 60 is just 240 degrees. And we would get that for both the cosine and the sine functions. And now we just need to simplify everything. So z to the fourth, we have 2 to the fourth, which is 16. And for the sine and cosine of 240 degrees, we can either use a calculator or we can just use the unit circle. Since 240 degrees would be right about here on the unit circle, that would be this angle. And we know that because 270 degrees will bring us to this negative vertical axis. And 240 is a multiple of 60. So we have a 30, 60, 90 right triangle where this is our 60-degree angle. So this one is our 30. We know the hypotenuse is 1, and the smallest side opposite this 30-degree angle here would be half the hypotenuse. So our horizontal component is negative 1/2 since we're going in the leftward direction. And our vertical component would be root 3 times by the smallest side. So it's getting a little bit messy, but this would be root 3 multiplied by half. And it is also negative because we are in the negative vertical direction. So the xy coordinate of this point would be minus 1/2 for the horizontal, or minus root 3 over 2. And we know that the x value is the cosine of the angle and the y value is the sine of the angle. So we can plug in our values for that. We have 16 for the new magnitude of our complex number, multiplied by minus 1/2 for the cosine of 240, plus I times by minus root 3 over 2. So actually, let's just subtract I times by root 3 over 2, and we can distribute the 16 to both of those. We get minus 8 and minus 8 root 3. And I encourage you, check this with your calculator, plug these in just to double check that these are right. But if you don't have a calculator, you can use the unit circle and draw this 30, 60, 90 triangle and just recognize that in the third quadrant, the x and the y value are both going to be negative. And comparing this to our answer choices, we don't actually have this in exact form, but we can see that negative 8 has to be a real value, so C is the only option. But if we plug this into our calculator, we will see that minus 8 times the square root of 3 is approximately minus 13.9.